Liquid to gas, if it is plus, the numerical value is not changing. For gas to liquid, only the sign changes. So the numerical value of the enthalpy change remains the same, but only the sign changes. So this can be defined like this. The change in enthalpy when a liquid changes into vapor, when a liquid changes into vapor state, or when a vapor changes into liquid state, it is called the enthalpy of vaporization. Similarly, you can think of enthalpy of fusion. Enthalpy of fusion means if you are taking water in ice form in solid state and you melt it and you want to convert 1 mole of the water in the solid state to 1 mole of water in the liquid state, what is the enthalpy change accompanied with this process is plus 6.02 kilojoule. And you are reverting, the liquid is converted into solid. The delta H becomes minus 6.02. Even here, there is no numerical value change. It is only the sign differs. And such conversion, it is a phase transformation. It is called enthalpy of fusion. So the plus sign indicates that the heat is given, that we are supplying the heat. The heat energy goes from the surrounding to the system. Heat energy goes from the surrounding to the system. That is plus. It is also called endothermic. Endo means going in. If the sign is negative, the heat is liberated. Heat comes out. It is called exothermic. Heat comes out. So this is enthalpy of vaporization and enthalpy of fusion. Similarly, the enthalpy can be studied for so many things: enthalpy of combustion, enthalpy of formation, enthalpy of crystallization, enthalpy of fusion, enthalpy of transition. For all physical and chemical changes, enthalpy can be calculated. But the enthalpy change is very important. But actual enthalpy, what is actually happening, what is the actual value of the enthalpy of a particular state is of no significance in thermodynamics. Mere H is of no significance. Only the delta H has very important applications in thermodynamics. Next, heat capacity. This is another important thermodynamic parameter. Heat capacity means it is the heat energy required to raise the temperature of a body by 1 degree. You have to understand this very thoroughly. See, I'm taking a substance and the temperature of the substance is say 20 degrees centigrade. I want to raise the temperature of that substance to 21 degrees centigrade. See, the difference is 1 degree. So from 20 degree to 21 degree. What is the quantity of the heat energy to be supplied? Or how many joule of energy is spent to raise the temperature by 1 degree? Or what is the quantity of energy in terms of calorie is supplied to raise the temperature of the body by 1 degree? And that quantity is called heat capacity. If it is measured for 1 gram of the substance, that is unit mass of the substance, then it is called specific heat capacity. If it is measured for 1 mole of a substance, it is called molar heat capacity. But in general, heat capacity C, look here, the heat capacity C between the temperatures at T2 and T1 is equal to the quantity of heat energy supplied Q divided by T2 minus T1. So this gives you per degree rise. What is the heat energy? Suppose T2 is a 40 degree, T1 is a 35 degree, means it is a 5 degree. But the heat is applied divided by 5 degree difference, then that will give you the heat energy required to rise the temperature of the body by 1 degree. So the temperature range is divided. So see, the heat capacity between the range of temperature T2 and T1 is equal to Q by T2 minus T1. So this can be written as dq by dt. See, if it is done at a constant volume, what happens? I'm maintaining the volume constant. So when the volume is maintained constant, for a gaseous substance, a gas is taken and it is put in a cylinder and you are raising the temperature and you want to find out the heat capacity of the gas, which can be carried out in two different conditions. One is at a constant volume condition and another one is at a constant pressure condition. You can either maintain the volume constant or the pressure constant. When the volume is maintained constant, there is no practically an expansion. As there is no expansion, there is no work done. So work done is equal to 0. So according to the mathematical representation of the first law of thermodynamics, Q is equal to, or delta U is equal to Q plus W. In this case, W is 0. So Q is equal to delta U. So I can write this equation like this. C, that is heat capacity at a constant volume between in the range of temperatures T2 and T1, it is equal to Q divided by T2 minus T1 at a constant volume, which is equal to, this Q is delta U now because the process is done at a constant volume condition. So it is only the internal energy change. So the heat energy which you have supplied is used to rise only the internal energy. So internal energy change divided by T2 minus T1 at a constant volume. So the CV can be written as dou U by dou T at a constant volume. Similarly, for a gaseous substance, the same thing can be measured at a constant pressure condition. What is it at a constant pressure condition? It is expansion. So I can write the Q is equal to delta U minus W. So Cp in the range of temperature T2 and T1 is equal to Q divided by T2 minus T1 at a constant pressure. So Q is equal to, in this case, delta U minus P into delta V because it is an expansion, which is equal to delta U plus P into delta V. So this delta U plus P into delta V, according to the previous slide, it is delta H, the enthalpy change. So at a constant volume condition, the Q, the energy supplied, changes only the internal energy. When the pressure is maintained a constant, volume supposed to change, which means the system has to do some work, which is the Q is equal to the delta H, the enthalpy change. So I can write Cp, that is the heat capacity at a constant pressure, is equal to the change of enthalpy divided by change in temperature. So which can be written as Cp is equal to dou H by dou T at a constant pressure. So in general, I can say heat capacity, when it is done at a constant volume for the gas, it is the change in internal energy per degree rise of temperature. That is Cv is equal to dou U by dou T at a constant volume. When the same thing is done at a constant pressure, change in enthalpy, it is heat capacity is the change in enthalpy per degree rise of a temperature. Cp is equal to dou H by dou T at a constant pressure. Any doubt you have?